Okay, now that we know some of the basic properties, we're gonna figure out the formulas that we're gonna use throughout the entire chapter. Now let's take a step back and think of the last couple chapters when we've done the force of electric, which equals QE. Now, unfortunately, we're not able to use a similar formula for the magnetic because electric is a monopole or magnetic is a dipole. So what we actually have to do is shoot an electron through the field to determine the force. So there's going to be a velocity of an electron added onto this. So the force magnetic equals QVB, where V and B are perpendicular. Now, if V and B aren't perpendicular and they're at an angle, we have to use a reducing agent because the force won't be as strong. So we use sine phi. Now, the max of force electric would be equals QVB sine of 90. Because sine of 90 would be 1, so we just get QVB. Where the minimum is QVB sine of 0, or we could use sine of 180, because that would just be, the whole thing would be equal to be 0. So now that we know this formula, when we look at it, anything with a sign kind of hints us to being a cross product. So we know Q is going to be a constant, such as the charge of the electron. It's always going to be the same. So we can't change the charge, or we can change the velocity, or we can change the magnetic field. So we could do Q, V cross B, and that's going to give us the force as well. Next, what we want to do is we can solve for B when when V and B are perpendicular. So then sine would cancel out. So FB equals QVB. And we can solve for B. So it's FB over QV equals B. And now that we know that, we can figure out the units for the magnetic field. So the units for FB would be newtons. And then the units for Q is coulombs. And then velocity would be meters per second. Now we can kind of play around with them for a little, and we can make it newtons over coulombs per second meters, because we know coulombs per second is an ampere, so we can do newtons over ampere meters, which is the same as a Tesla.
Okay, so now we're going to connect everything that we just did with a small example. It goes back to the idea that opposites attract each other and then like things repel each other. So let's say the classic example, you have Lenape on one side and then you have Shawnee on the other side. The two schools are close to each other, only separated by a window. So you have, let's say you have the Lenape boys against the window, and then on the other side are the very attractive Shawnee girls. Since they are opposites of each other, they would attract each other, so both of them would be closer to the window. So let's give you another example. Let's say you have Lenape boys on one side, and then you have Shawnee boys on the other side. Since they're both the same, no attractions, they're actually trying to get away from each other. They rather see the girls and not the guys. So you can think of that as another example. So as many of you should know by now that the Earth's magnetic field is produced from its core, which is the center. And scientists often use this idea to create compasses, which obviously leads you to the direction north. So what we see here could, at first glance, may seem like a contradiction. You have here your bar magnet, which acts as your compass, and it is pointed directly north, to the north, which you would seem as a contradiction because, as we've just stated, that opposites attract and likes repel. So with that in mind, you would think that the south should be up here. But in fact, there's a distinguishing factor that we should also consider, that this part is actually technically the south pole of the Earth's magnetic field, and then this side is the north pole of the Earth's magnetic field. This is only the geomagnetic north of the Earth, and this is technically only the geomagnetic south of the Earth.